So in this last video, we're actually going to write a script which calls the function that we just wrote, modified to also return the time values for these three particular combinations of resistor and capacitor values. And remember, in function language, these are called input parameters. So how do we actually do this? Well, let's go back to MATLAB, right? We already got our nice function written here. I can close the figure by either clicking the X out on the tab, or I can just type close all on the command window. So now I want to open I want to write rather, not a new function, but a new script. So notice that you don't have the function header in this. So let's think about what we actually want this to do. It's always good to start when you're writing software by adding comments of what you're trying to do. So I'm going to add a comment that says call for first combination of R and C. And remember, we're doing this 3 times basically. So I'll say call for the first, call for the second, call for the third. And then if you notice, the last thing that it wanted us to do is to actually generate a plot on the same plot. So I will then say plot all 3 current values. So how do we actually call this function? Well, you already know how to do it because we already did it on the command line. So I would just hit up and I would copy exactly what I just typed down there. And I would just make sure that the values are the same in each case. So leave the voltage source alone at 1 volts. We want the R value to be 1 times 10 to the third, the C value to be 1 times 10 to the negative 6 for our first combination. So one thing that we definitely want to modify is we'll call this T1 and we'll call this I1 because we're going to be storing different time vectors and current vectors for different resistor values. And you could, to make this more readable, actually define these resistor and capacitance values as variables as well. Like you could call this R1 and you could call this C1 and so on. But since we're already in a long lab, I'm just going to do this quickly. So I'll modify the output variables that each function is returning with a 1, 2, and 3 after the fact to keep them stored separately. Okay, and then what I want to do is actually make the plot. But it's always good practice when you're doing this, and make sure to update your component values, right? I didn't do that. The first combination, R 1 times 10 to the third, C 1 times 10 to the negative 6, that is good. But in the second, we want R to be the same, but we want C not to be 1 times 10 to the negative 6, but rather 2 times 10 to the negative 6. So make that modification. And then notice in the third combination, we want C to go back to the original value, 1 times 10 to the negative 6, but R to go up to 2 times 10 to the third. So I'll make that modification. So usually when I'm writing a script, well, just actually save it and call it something. I'm zoomed in so you can't see. So I'll call this my lab 2 script. And then I will run it, which I can do by either typing the name here on the command line or hitting the run button. And I basically just make sure nothing breaks. So I would expect that this won't produce any output because all 3 of these function calls are terminated by semicolons. And if you execute it, it doesn't produce any output. However, it is placing these values here in your actual workspace. So you know it's all good. Now you might look at this and say, where did I and T come from? I didn't return any of those. That's why sometimes it's good practice when you have a script to clear your workspace at the beginning. So if you add clear all at the beginning, it will start by wiping this workspace, which would have got rid of the I and T that were left over. And if I re-execute this, notice that I only have I1 through I3 and T1 through T3. So in order to plot all these values, what I need to do is call the plot function. I'll begin by plotting T1 and I1. Usually I will just run at every step to make sure that it works. This is memory. This is not efficient from a computation or memory point of view because I'm remaking all those computations every time, but that's okay. The way that you actually, so you could just, I'll show you how I do it in a minute here in actual practice. But in order to generate a new line curve on the same plot, you'll need to use hold on to make that happen. Then we'll plot the second combination of time and current values. So what I was saying is, even though I have this all in the script, oftentimes I'll just copy the section of the code that I want to run, and I'll paste it directly on the command line. And the reason that works is, remember, all the vector values you need are still defined in the workspace. So if you notice, I have my original plot here along with my new plot. Now let's think about what's going on here. In verse 1 versus 2, the only thing that changed is the capacitor got twice as big. Now, physically, what's going on is that if the capacitor is twice as big, it takes twice as long to charge it up. So if you notice the curve in red here, the blue one's the one we had originally. We probably want to put a legend on it. We will here in a minute. The red one is the new one we generated. It takes longer to charge up because that capacitor is bigger. Now, when we actually generate the third one here, what do you think is going to happen? Well, let's actually run it and just see. And usually when you're generating multiple plots, it's a very good idea to close the prior plot, especially when you have the hold on, because if not, it will just draw 3 curves over top of those 2. But since we have these values in memory, we'll just re-execute the plotting portion. And you see that we have our actual 3 curves now. And what's different about these? Well, wouldn't it be nice if we had a way to actually see which one was which? So the way that you actually label a legend on your curves in MATLAB is to use the legend command. And then you pass in actual what are known as string literals. So actually the text that you want to plot on the actual graph to label each individual curve. So in the legend, I'm going to call this trial 1, and this will be trial 2, and this will be trial 3. And we can probably give them a better name later on. You could rerun the whole thing, but actually since that plot is currently active, if you just execute the legend command, it'll put the correct legend on there. So if you notice, there's our first trial, and the red is our second trial. We already analyzed the difference between those. The only difference between the blue and the red rather, is in the red, the capacitor gets twice as big, so it takes longer to charge. And what's going on in the actual third trial here, which is this yellow type curve? Well, if you notice, the resistor gets twice as big. And when the resistor gets twice as big, remember that this peak value, its value was V divided by R. So if all 3 cases, if V stayed the same, here's that formula here. If Vs stays the same, if R gets twice as big, that peak value is going to cut in half. So that's why that peak value is down here. However, if you look at it, as you go out in time, the red curve and the yellow curve kind of start to align on top of one another. Well, why is that? Well, if you go to the actual values here, and I'm going to close this plot, for the first curve and the second curve, if you take for the second curve and the third curve, if you take the product of R and C, they're the same thing. So just to kind of rerun all this, I'm going to clear it all, then run it all from the start to show you how it works. But what we're doing here is we're looking at the trial 2 curve and the trial 3 curve, and you notice that even though they have different initial values, once you get to a far out enough in time, they start to lie over one another. And the reason is, if you take the RC product in both cases, they're the same. So they have the same time constant. So they both take the same amount of time in order to charge the particular capacitor. The the transient period is over in the same amount of time in both cases. However, these initial values are going to be different because the resistor values are different. So all that I'm looking for in this one is an actual your code here. So paste your code below. So just to show you what I mean by this, literally just take this code from MATLAB, open up a Word document, paste it in here. So you can say, like, here's my code, and then give me this screenshot, which you can do through a traditional like snippet tool or just print screening and then cropping it in Paint. Or if you want to be really formal, you can actually save it and insert it as an image. But for me, like if I were you, I would just print screen it. I would go to Paint. I would put it here, and I would just crop. And that is all that I'm looking for. If you want to be like, if you really have a lot of desire to learn plotting in MATLAB right away, do a better crop than I did there. And you could crop it in Word, of course. But you might want to put labels on the individual axes. The way that you do that, the function to put an X label on is called X label. You pass a string of whatever you want to label that axis in. So I'll just say this is time measured in seconds. And the Y label is going to be current measured in amperes. So notice now if I close this again, actually I'm not going to close it just to show you what happens if you don't. Notice how the colors get messed up? That's because it's generating a new plot over the old plot. So usually that's why a lot of these scripts at the top that are kind of computational and visualization in nature will have clear all and close all at the top to close any plots, clear the workspace, that way no old computations get to you, and then generate the actual family of curves that we're interested in including there. So hopefully that made sense. I know it's kind of trial by fire, kind of a lot of video and a lot of different code that we wrote, but that's the way that you actually get this stuff down. You have to, there's no secret. Like the kind of funniest thing in the world is to think about teaching someone to code. Really, that's why these are really, really tough classes to teach online. but we're going to keep having these mix of labs where we actually kind of just follow me as I go along with my coding, and the actual lectures where we talk more about the theoretical aspects of computing for engineers.